So, element 117 officially joined the periodic table in 2016. The name Tennessine was chosen to reflect the contributions of the Tennessee region to the discovery. The ending, INE, is characteristic of column 17 elements like chlorine, fluorine, and now Tennessine. In fact, you would have thought perhaps that the name would have been Tennesseum. That's what we're used to in terms of new elements. But the chemist told us, oh no, group 17, this has to end in INE. The result could not have been achieved without international collaboration. And this required unique facilities both in Russia and in the United States. It also required a team of physicists, chemists, and engineers of more than 100 in both countries. Adding a new element to the periodic table is very exciting and also a significant scientific accomplishment. But the element 117 discovery was much more than that. It also advanced the understanding of nuclei with extreme numbers of protons and neutrons. Including the decay products from element 117, 11 new nuclei were added to the nuclear chart. And it also foreshadows the discovery of even heavier elements. Element 117 is a so-called super heavy element. This term refers to elements with more than 103 protons. It was Seaborg who predicted the existence of super heavy elements in the 1960s, and he realized that new facilities would be required for heavy element chemistry. And so he proposed the development of a high-flux reactor and radiochemical processing center at Oak Ridge National Laboratory to advance this research. And his vision turns out to have been very important for this discovery, which comes more than 50 years later. Seaborg also predicted the existence of an island of stability for super heavy elements. You may recall from high school chemistry that atoms with closed shells of electrons are more stable. Think the noble gases. Well, it turns out that nuclei have shells of protons and neutrons, and those nuclei with closed shells of protons and neutrons have stronger binding. The last stable isotope, lead-208, has a closed shell for both neutrons and protons. Well, we can imagine, we can calculate where the next closed shells would be. Can we get there? And if we could get there, what would the lifetimes be? Some theories predict that the lifetime would be millions of years. It's very exciting. So we are on a journey not only to discover new elements, but also to find long-lived elements beyond the known periodic table at the island of stability. So what are the key questions? The key questions are, where does the periodic table end? We don't know. What is the limit of the number of protons and neutrons a nucleus can contain? We don't know. Do super heavy elements have special nuclear properties and special chemical properties? We expect so. And does the predicted island of stability exist? And one of the important results of this work is a very strong indication that it does. So how do you make a super heavy element? Well, you can do it around your kitchen table. All you need to do is find a combination of two atoms that when you combine their protons, they add to the number of protons you want in your new element. And then you smash these two atoms together in a high-energy accelerator. And for element 117, an intense beam of a special isotope of calcium was directed at a berkelium target. Now, berkelium is an artificial element has to be made artificially at an energy of around 250 MeV. Now, if you look at the representation at the bottom of the slide, we're starting with a calcium-48 nucleus, which has 20 protons. We're impacting it on a berkelium-249 nucleus, which has 97 protons, and 20 plus 97 equals 117. So on rare occasions, these fuse. They create a compound nucleus in a very excited state. And the trick is for that compound nucleus to survive long enough that you can discover the new elements. So in our case, the choice of the calcium-48 and berkelium-249 was key, because these both have very large excesses in number of neutrons. So that compound nucleus has many extra neutrons. Before it can fly apart, it sheds energy by shedding those extra neutrons, and that's why element 117 exists. So what did it take to produce a few atoms of element 117? Well, you remember the calcium-48. It is a naturally occurring isotope of calcium, but it's very rare, so it has to be enriched by 500 times. Then you need to produce 20 milligrams of berkelium-249, an element that does not exist in nature. This was produced by neutron irradiation over almost a year in the world's highest thermal neutron flux at Oak Ridge National Laboratory. This is followed by a very delicate chemical separation, because what comes out of the reactor has lots of stuff in it, and it's very radioactive. This chemical separation has to be done behind 3 feet of concrete. It takes about 6 weeks, and the final material has to be purified to 1 part in 10 to the 7. Then you have to produce targets that can survive heavy ion beam irradiation, and then you actually irradiate those targets for 150 days in the world's highest, in the world's most intense calcium-48 beam, which is available at the Fluorov Laboratory in Dubna, Russia. The major facilities at Oak Ridge and Dubna were essential to this experiment, and what's pictured here is the heavy ion cyclotron at Dubna and the reactor chemical separations complex at Oak Ridge, the same complex that was Seaborg's vision. More than 100 scientists and engineers contributed to the discovery. This includes scientists from Dubna, from Oak Ridge, from Lawrence Livermore National Lab, from the University of Tennessee, and from Vanderbilt, and from the University of Nevada. In addition, more than 100 technical staff at Oak Ridge and at Dubna were needed to support the berkelium production and the separation and the accelerator campaign in Russia. Pictured are the scientists and engineers who performed the chemical separation at Oak Ridge, and in the circle is actually a picture of the 20 milligrams of berkelium that was produced. It's that little green dot, if you can see it, at the very bottom of the glass vial. So 6 atoms of element 117 were produced in the first campaign. How did we know we had element 117? Well, we produced 2 isotopes of element 117, one with 177 neutrons, the other with 176. These isotopes decay into 9 additional heaviest isotopes of elements 115, 113, 111, etc., by sequential alpha particle emissions. This decay chain provides a unique signature for element 117. The likelihood that that sequence of events could be produced at random is less than 1 in a million. Now, we talked earlier about the island of stability. And as we approach it, we expect the lifetimes to increase. So the element 117 experiment provided an opportunity for us to test this by looking at previous data and the new data from the decays of element 117. So for a particular isotope, for a particular element 113, we now have a span of isotopes spanning 8 neutron numbers from the lightest to the heaviest. What happens as we add neutrons to that element 113 isotope? Well, the lifetimes are going up. And over that sequence of 8 neutron numbers, the lifetime actually went up by a factor of 7,000. You would have expected, without an island of stability, for the lifetimes actually to be going down. And so this is the strongest evidence we have to date of the existence of the island of stability. The data that we got is very consistent. You can look from these charts at how well it fits. The areas outlined in blue is the new data added from these experiments. So it's a significant increase in our understanding of the nuclear landscape for the heaviest elements. And it also continues the trend of increased stability for increasing neutron numbers. Now, we got a bonus when we discovered element 117 because we also discovered element 115, which is a decay product of element 117. So we got 2 for 1. And it is very fitting that the names chosen for these 2 elements were Tennessine in recognition of the contributions of Oak Ridge National Lab, Vanderbilt, and the University of Tennessee, and Moscovium in recognition of the contributions made by our collaborators in Russia. There were 2 other elements that were named at the same time. Oganesson, which is element 118. It is named for Yuri Oganessian, who is the scientific leader of the Fluoroff Laboratory and the key partner in these experiments, excuse me, and nihonium, which was discovered in Japan. Yuri Oganessian is one of 2 living persons who has ever had an element named after him, the other being Seaborg. So in summary, 2 new elements with atomic numbers 115 and 117 have been synthesized. They demonstrate increased stability with increasing neutron number. Longer half-lives will enable single element chemistry on these new atoms. We are at the shores of the fabled island of stability. And new elements up to element 120 are within our sights. The next steps, let's go to higher atomic numbers. Let's go to higher neutron numbers. We are working now on special isotopes of element 118, which would be the heaviest nuclei ever produced. And we are searching for new elements 119 and 120. Super heavy elements are important because they offer the potential for new physics, new chemistry, and new material science using atoms previously unknown that have extreme numbers of electrons, protons, and neutrons. Element 117 is a very significant step toward that island of stability. And the continued progress in this area rests on the shoulders of a community of scientists and engineers who harness the power of international collaboration. Thank you, and the last is the latest version of the periodic table. Thank you.